Hello, friends, and welcome to Open Source LLMs at Global Hack Week. My name is Will. I am a software engineer at Google, a coach at Major League Hacking, and one fun fact about me is that I am feeling quite sick today, which is kind of a bummer. In fact, I just took a COVID test. Turns out this one says negative, which I think is good, but we'll probably have to retest because I hear the rapid antigen tests can be relatively high rates of false negatives. Thank you. Yeah, that is my kalimba. I think it's been a long time since I've done a Global Hack Week stream without playing the little kalimba intro. So it is tradition at this point. But welcome. I'm super excited to hang out with y'all and talk about large language models. This is a topic that I think is super interesting. We are going to talk about a little bit about when we say an LLM, what different kinds of models are we talking about? We'll talk about encoder models, decoder models, encoder decoder models, and we'll also talk about different ways that you can try to get an LLM to do what you want. So we will talk about different prompting strategies and fine tuning and all that sort of stuff. And we're going to do it through the lens of this project that I just worked on at Kaggle called the Kaggle LLM Science Exam. Hello, King C. It is good to see you. I believe I have seen you on streams before. Your username seems familiar. Before we get going, let me know where you're tuning in from and what the weather is like where you are. I am in Seattle, and it's been cloudy, but not particularly rainy today. It's been pleasant. Hello, Micah. Good to see you again as well. We will probably just vamp for a few more minutes and let anybody who wants to show up. Also, classic beverage check. I am drinking water. This morning, I started with a cortado, and then I wanted more coffee, but I didn't want more espresso, and so I made myself a pour over with some coffee beans from Mexico. They were very tasty. Near Vancouver, a bit rainy also. Oh, Vancouver, not that far away. Oh, I love to hear that. Yeah, so for the Web3 Global Hack Week, because I don't really do like proper Web3 things, but I do like goofy machine learning projects. So we tried to predict the price of a CryptoKitty based on the photo of it. I'm thrilled that you got enough value out of that project to put it on your resume. I think that's just the sort of closed loop of like, here's a problem and I went and got the data and I built a model and like now I can, predict a thing for you is a very neat kind of project to see. So that's great. Here from LA. LA weather equals fire. That's fair. Are y'all still in like forest fire season formally, or are you just saying it's still hot? Because I think that in Seattle, it's been a while. I've been told that the Seattle forest fire season doesn't actually end when I think it ends. It's just that the wind starts blowing the other direction, so I don't smell it. But I feel like we've wrapped up our fire season in Seattle. In from India, very much appreciate you being here because I know that means you were up at a kind of gross hour. So appreciate the dedication. So maybe we'll start off before we just dive in. 5 a.m. Wow. Yeah. Are you normally an early bird, or will you just get up for Global Hack Week things? I'm curious. I would also like to know from everyone. I'd love to get a sense of. Also, apologies. I have a cough drop in my mouth, sickness as mentioned. But if it makes my talking weird, then let me know and I will try to adjust. But I'm really curious to know, everybody who has shown up today, what our general level of familiarity with large language models are. So I would be particularly interested in like, what if we do like a 0 to 3 rating, where 0 is like, I don't know what an LLM is. And maybe a 1 is like, yes, like I have used ChatGPT, maybe I've played around with Bard. A 2 is like, yeah, like I actually have fine-tuned these things. I have experimented with different prompting techniques. I'm kind of in on it. Like I know the parameter count of these different models. And then a 3 is like, I am an AI researcher. Like I created the transformer. Let's get some ratings down there. I would say that I right now am at a 2. I did not invent the transformer model, but I have played around with these things a little bit more deeply. Okay, great. A lot of ones. Honestly, a one, we got a 1.5. 1.5, that is a perfect range. I mean, if we had zeros, that's totally cool. You could say zero, but if you have no clue what it is, you might have to do a little bit more conceptual work about this is what a large language model is. We can kind of focus today on going from sort of one to two, going from I know what these things kind of are conceptually, and I may have used them, but I've never really like opened the hood and poked around. And I think our 1.1s and 1.5s will be in good shape as well. So I will drop a link to a notebook that we'll be working from today. Okay, cool. That's good context to have. This is a big thing. There's lots of folks that come from, I've done machine learning either on images or on tabular data, or maybe even on like audio or video. And language is like, I mean, I think that recently we've both seen an explosion in growth, a lot of areas of machine learning. I feel like we've also seen this divergence that it's like, well, hey, there's, you have diffusion models doing a lot of image stuff, and then you have, large language models, and then we're doing more multimodal stuff where you can, go from a text prompt to an image, or ask a model what's going on in an image. But it's like those areas are both getting bigger and kind of more distinct, which is interesting. Okay, cool. You used an API that is definitely like getting a little bit closer to the to sort of what's going on under the hood. That's cool to hear. So we are going to be using this project that I really have just wrapped up at Kaggle. So at Google, you can spend 20% of your time doing a separate little project. So my main work is on Google Cloud, but I spent my 20% time on Kaggle doing these machine learning competition projects. And I will pop into this view. So the link that I just dropped should take you here, which is the notebook that basically I will be working from today. But you can click through on this link right here. Actually, I should maybe do a few minutes on Kaggle. So Kaggle is I think it is the largest data science and machine learning online community in the world. It is mostly a place, at least in my mind, the main thing that Kaggle does is it hosts these competitions where a bunch of different people will try to build their best AI, their best machine learning model, and they will sort of pit them against one another and see whose model is the best. And you can win money on here, you can win fame and riches, and it's very cool. And so I just finished running this competition called the LLM Science Exam. And the challenge here was, you can click over here onto the data tab, which I can drop this link as well. Ooh, okay, I want to come back to this question because this is a good one. And on the data tab here, and you can see if you click on train, my screen's probably a bit small, isn't it? Let's not click in a few ticks. You have questions. So you have a prompt that is basically a science question, and then you have A, B, C, D, and then there's E, and you have to produce the correct answer. So you have to look at this difficult science question and answer it. So we can just look at number one because it's small enough to fit in the text box here. Which of the following is an accurate definition of dynamic scaling in self-similar systems? And if that reads to you like gobbledygook, you're not alone. I generated this data set, but most of the science in here I am not an expert in. But we could search for this. Dynamic scaling, cool. Now, what are the answers like? Dynamic scaling refers to the evolution of self-similar systems. Okay, well, we won't dig in and actually answer this question, but we have this data set of really difficult science-based questions, and the question is, can a large language model answer these questions? And so usually the way that people submit to these is that they will write code within Kaggle that builds a model to do this task. And that's what we're going to do today. We're going to, inside a notebook, and we'll talk more about what a notebook is if it's unfamiliar, inside a notebook, build our own large language model to answer this question. But first, another question that came up, I guess we had someone second it as well. Do I need to be good at math for machine learning AI stuff? I've heard a lot about that. So this is a great question, and the answer is kind of yes and no. There is a spectrum from the sort of cutting edge of AI research. You will probably need a PhD to be doing this, and that PhD is probably going to involve a decent bit of, at very least, some calculus, and some matrix algebra. Probably some more, obviously a lot of programming. And then on the other hand here, there is the world of sort of machine learning engineering, taking all of these machine learning Lego pieces and sticking them together. And I think at all levels, it can be kind of helpful to have a conceptual understanding of what's going on, even if someone mentioned they were just using the OpenAI API. So this is, you call a function basically with your string, and it returns to you back a string of what the model responded with. Even in that situation, kind of understanding the concepts behind machine learning can be really helpful. But there's not a lot of math the math of large language models is not something that you really need to understand that deeply. And then as you come over to the other side, you maybe go through the, hey, I'm fine tuning some models, doing some more of what we're going to do today. And in that case, knowing some math can be really, really helpful, but rarely it's like you're never going to sit down and have to work out a math problem. You're just going to have to kind of understand what things are, right? So like, for an example, I don't know how to do long division. If you gave me, 1,286 divided by 13, it would take like I could probably reinvent how to do long division, but it would take me a long time to do that, on pencil and paper. But I understand the idea of division, right? I understand it's okay. I'm trying to take this one number and and sort of divide it into this many groups, and how much is in each group. And I think that's the sort of conceptual understanding that's really, really useful when you're sort of in the middle there. And I think traditionally, if you're going to do a PhD in machine learning, yeah, you should have a pretty good basis in linear algebra, matrix algebra, and calculus. I will say, just based on papers that I have been reading that have been coming out of machine learning labs, there's been an interesting shift where even a lot of the people doing cutting edge research here have stopped worrying quite as much about what is happening at sort of the very low mathy level, and are now a little bit more concerned about these emergent behaviors, like questions like, is your LLM likely to be cooperative? Which, like, is that a computer science question? I don't know. Like, people are asking this question in a computer science department, in an AI ML research lab. But that kind of feels almost like a psychology or a sociology or an econ paper, right? So there's a lot of like interesting, wacky stuff happening at the forefront of research. So I would say that it's always helpful to have a conceptual understanding of the math. Almost never do like you have to do an integral in doing AI research. And I think that more and more, a lot of the interesting questions are getting not less mathy, but a little bit less in the weeds with the math. I don't know if that answers the question. I think you should definitely try to understand sort of relevant math. But if you're like, hey, I just don't want to be doing integrals every day for the rest of my life, definitely there's a lot of work going on in machine learning that is not that. The ML AI roles I've seen, they require MS or even PhDs. I assume it was very math heavy conceptually. Yeah, I do think that there is more and more. I think it's an interesting time, honestly. I think there are more and more pieces of interesting work to do that still people who are listing jobs are like, yes, I'd like the person who's going to do this job to have a PhD, mostly because that is a signal of, you really have spent the time to understand a space. And I think that there are a lot of things that are being done by PhDs right now that could be done by sufficiently motivated CS undergrads, say. But also, I'm not the ultimate authority here. This is sort of my based on what I have seen in the industry, it feels like we're moving to a place where, like in some ways, the machine learning PhD is becoming like more valuable, and in some ways, it's becoming like less applicable. I think a big thing you've seen is people with PhDs realizing the second that they finish their dissertation, it is like instantly out of date, and they have to just scrap it and say, okay, I have this machine learning PhD, and it is not really going to actually help me at all, which is a little bit sad. Someone asked how did I place in the Kaggle competition. So I was not allowed to compete because I came up with the data source. So I did not submit. I do have a submission as a starter submission that we provided to people that was like purposefully very, very basic. Yeah, cognitive science, definitely. Like there's a lot of interesting like theory of mind work being done. There was this paper on making large language models play the game Hanabi, where you have to have a model of what the other players are thinking that you're thinking, and you could do a lot of interesting research there. Let's see. That's wacky. It is wacky. Hello. Oh, hello. It's good to see you. Philsobi. said, what are some resources for those ML papers? So if you're looking for broadly to like get into reading ML papers, there are two big resources that I would recommend. We can actually pop back over here. We've just been having a good time chatting, which I promise we will actually get our hands dirty with some machine learning in a second here. So one is paperswithcode.com. This is a really, really great resource that highlights really big, important papers in machine learning that have published all or some of their code or data. So one method you can use here is if you click over to methods, this is sort of like the big ideas in machine learning. So the idea of attention, I'm sure many people have heard this idea that the big thing behind transformer models is this idea of an attention mechanism. And so you can click through here and you can look at the study of attention. And then you can see right up here, this is like the main paper. This was the paper that invented the transformer architecture called Attention is All You Need. And if you click on that, you can read the paper or you can see the code, and it sort of gives you an overview of it. So Papers with Code is great, and I really support it. The other one is this site called Semantic Scholar. This is not just machine learning related, but it is a good way to find things that you're interested in. So, you can search for LLM cooperation, and we can see if we get any good hits. Okay, cool. Yeah. So if you're interested in like multiple LLM agents like interacting with one another, boom, here are some great papers on it. One thing that is cool is you can see both the number of citations. So, okay, it's kind of a bad metric, but usually more citations equals more better. Or at least more influential. So this one has 19 citations, not a ton, but more than some of the other ones. But then you can see this is how many citations it was sort of influenced by versus just background citations. And so it's a good way to navigate going from one paper to the next. And that is semanticscholar.org. Oh, and without that backslash, I'm sure. But incredible questions. Love this conversation. The energy is great. And I think on that note, we're 15 minutes in. Let's just jump into the sort of core content here. So we have talked about our sort of problem statement here. Also, I should warn the LLM science exam has closed, so we can still use the data and play along with it, but you will not actually have the ability to compete in real time. But I'm sure this will be great preparation for the next Kaggle LLM science exam. So I will drop this link one more time, which is a link to a Kaggle notebook. And a notebook is kind of like writing a program, but is specifically these little cells that you can run and change and rerun. And so that allows you to experiment really quickly. This is functionally, it's like Colab or Jupyter Notebooks. These are all sort of the same idea. And honestly, the underlying infrastructure is basically identical. So I believe you have to create a Kaggle account to do this. It's really quick. I think actually you could just log in with your Google account because Kaggle is owned by Google, as previously mentioned. And you should see a button here that says copy and edit. For me, it just says edit because it belongs to me. But if you click copy and edit, you should see a view like this. It takes a second to load up. So our main editor here will have these individual cells, and the cells can be bits of Markdown, which allows you to, write pretty formatted text. And you can come over here and I'll click Shift Enter, and that will basically run the cell. And when you run a Markdown cell, it looks all pretty. But over here, this is some code. You can click oh, come on. A plus code button right there. And so the most basic thing we could do is we could just print out hello. Oh, hello. And you can see hello. And I press Shift Enter, but you could also just come over here and press the play button and it'll print it out. You can right click to delete the cell if you want to. And so this is all code that I've written that you can kind of take and play with. So in our competition, if you click over here under input, you can see that we have a training set and a test set. Now, in this actual competition, our training and test set are basically the same. The test set just doesn't have the answers. But we can import our training set into a data frame. Is anybody unfamiliar with Pandas data frames? Because if we are not familiar with Pandas data frames, I can dig into that. I'll admit we had some unfortunate scheduling. On Thursday, I am doing an intro to Python, and I originally thought that the intro to Python would be happening first, and I would be able to walk y'all through pandas, data frames, and Python in general. But if we have questions about pandas, data frames, okay, great. We have a few NAs. Are y'all familiar with Python? Have you played with Python, just not pandas before? Okay. Cool. In fact, I don't think we end up using pandas that much, but the basic idea is that pandas allows you to go from a CSV or like an Excel spreadsheet and bring that into Python in a way that's super easy to work with. So my 3-line example of pandas is we can import pandas as PD, and then the main thing we'll use is called a data frame. And so one way of creating a data frame is you can just have a dictionary of a bunch of columns. So our column name could be age, and we can have a list of ages. And then our next column could be called height. And we could say, maybe this is height in feet. So maybe our 14-year-old is 5.5 feet. Maybe our 21-year-old is 6 feet. And then our 6-year-old, I don't know, how tall are 6-year-olds? 3.5 feet? That sounds good. And we can store this in something. Oftentimes we'll use the variable df. And when we create this in another cell, we can say df.head, and that will show us what's inside there. And look at that. We have a nice little Excel spreadsheet-like object called df that has our age and our height. Cool. Yeah, so it is not, so a dictionary in Python is more or less the same thing as a JSON object in JavaScript. Once you turn it into a data frame, it specifically has a lot of functionality around it that lets you manipulate the data really easily. So a data frame is a little bit less like a JSON object. But I mean, certainly they're all collections of data, so they have some similarities. We have a question. Would you say that with all the hype around ML, AI, that it will be a requirement as a software engineer? So I think I have two different thoughts here. One is I think that using AI and machine learning in the process of being a software engineer is going to get very, very common. I mean, already, you have really, really good autocorrect. I have had experiences with editor copilots that, that I will type like 3 characters and it'll just auto suggest the whole file I was about to write. And so I think that's just going to become very, very common. I do think that you will see probably the growth of people who are deploying machine learning solutions. I don't think that you are going, if you have not majored in machine learning, or if you have not taken a million machine learning classes, I don't think that is going to be a detriment to being a software engineer. And I don't think that overnight all software engineers are going to be doing machine learning, right? I think that I think that most software engineers are thinking about machine learning these days, but I do not think that every software engineer is going to turn into a machine learning engineer overnight. Cool. So that's our brief little bit on pandas. So we can use this to import our training data. And this is just what we saw earlier. We have our prompt, which is sort of the question, and then we have the options A, B, C, D, and E. And the last column we have here is our answer. We can then turn our training data set into a data set. Sorry, we can turn our data frame into a data set object from Hugging Face. So Hugging Face is sort of the main course here. Pandas is just a way of slurping in our data from the file. But Hugging Face is, and I'll actually totally suggest as you can see all of the Hugging Face errors I've been looking into. Hugging Face is a giant repository of open source models. So this is really the main event here. This is where you can get models from out on the internet and use them for your own purposes. And this is a lot of libraries from Hugging Face is what we'll be using today. So do you use ML in your day-to-day work? Some companies are using it for cloud right sizing, for instance. Yeah, so I think that there are kind of what I was getting at earlier is that there are lots of different ways you could say that you're using machine learning, right? There are, of course, like lots of tools that I use to do my work. I mean, everywhere from like, of course, when you Google something, there's like a lot of machine learning behind that query, and I Google things all day long. But also, I will use a code copilot where, as you are typing, it is suggesting the next 7 lines, and you're like, oh yeah, that is the next 7 lines I was going to use. But then there's a question of like, are you working on new machine learning things? And I will say that in my work, I do quite a bit of data analysis, and so there's like always that fuzzy boundary between are you doing data science or are you doing machine learning? And this is like the dumb. It's not even a joke, but like the thing that I will say sometimes is that like the simplest machine learning model you can do is literally just taking an average. If you are trying to predict, for example, we'll go on a little tangent here. If you are trying to predict the height of a person, say we have an elementary school, and you want to predict the height of a person in that elementary school. Well, one way you could think about this is if you're just going to guess one number for everybody, the mean, like the average height, that is going to be the least wrong guess for every person in the school, right? If any number that you could guess would be more likely to be close to the correct answer, then that would be the mean. And so a thing that you could do is you could say, well, hey, I'm just going to take a lot of samples. I'm going to ask a lot of people their height. And then I'm going to approximate whatever the average height in the school is from the little sample that I have. Right. And because this model has one parameter, right, which is your mean, and the more people you talk to, the more data you get, you are essentially training your model with additional data, and your model is going to get better because your average estimate is going to be closer to the real average of the school. This is a little bit like when people talk about machine learning, this is obviously not the thing that they are thinking of, but there is like a big spectrum of, I will sometimes do clustering things at work because I'm trying to make sense of data. Occasionally I will use LLMs to make sense of log data, so things like that. And then, of course, with my 20% work at Kaggle, I'm actually actively coming up with, well, this would be an interesting way to test the capabilities of large language models. So sort of a lengthy answer, but that was the answer to, do I use ML in my day-to-day work? Ooh, okay. This is actually a really, really good question. Also, good to see you, Skull Crusher for Life. Definitely seen you before. Yeah, so accepted standards that are used, like DF is always data frame with pandas. So the thing that you were talking about, and this is not a word that I knew until someone was like, oh yes, this is the thing, is Python idioms. So there are a list of Python idioms, and people talk about idiomatic Python, which is not like it's not like that's right, but that is the convention. I'm actually kind of curious. I think you pick these up as you just write Python and read other people's Python. You'll notice like, oh yeah, like I think that importing with aliases is a really common one. You'll notice like, oh yes, everybody imports NumPy as NP. I didn't know that, and now I do because I saw someone do that. I am curious if we just hop over, like list of common Python idioms. You'll also have not just like this is the common thing you import out. You also have the idea of like Python conventions. So yeah, here are just like there are lots of like tips and tricks that fall under this category as well. List of common Python import conventional aliases. Are there standard aliases? There is no canonical list. This is really zoomed out. There's no canonical list, and I wouldn't advise making one here. SO isn't really the place for that, in their humble opinion. Yeah, interesting. I do think it is a good question. I think it is one of those things that, yeah, over time you just notice what people do, and I don't know. I think it's a reasonable thing for there to be a list, and I'm sure someone has compiled like a lot of common ones. But of course, one problem with Python is that your Python is different from my Python. I'm using Python to go and host a website, and someone else is using Python to do a lot of what is functionally shell scripting on their server, and then someone else is using Python to do data science, and someone else is using Python to do scientific computing. So I like the list I would come up with would include, oh yeah, NumPy as NP and Pandas as PD, and I probably wouldn't think to include some hardware library. But no, reasonable question. Okay, back over to our prediction. So we have pulled in our data, and now that we're actually going to pick a model out. So we're turning our data frame into a data set. All you have to know is that data sets are specific to Hugging Face. It's sort of their object that wraps around a data frame that makes it useful with a lot of their libraries. But I think now it is a good time to talk about different kinds of models. So this is just going to focus on transformers and natural language processing. So, it's totally possible to use a transformer on image data, and it's totally possible to do natural language processing with different architectures of models. But here today, we're just going to be looking at transformers used for natural language processing. And broadly, there are three kinds of three kinds of transformer architecture. One is called an encoder-only model. And the sort of general idea that I would present for an encoder-only model is where you're going from a bunch of text and you basically want one simple answer. So you feed in a bunch of text. I mean, one classic example here would be sentiment analysis. You feed in a bunch of text and you just want your model to spit out one number that's like positive if the sentiment is good and happy, and negative if the sentiment is bad and morose, right? That is just an encoder-only model where you push in text and it spits out a few numbers, generally speaking. You also have a decoder-only model. And this is where your model is spitting out text. So GPT, all the GPT models are technically this, and they are called autoregressive decoder models, where you kind of see all the text the model has written before. And so it'll write one word, and then it'll say, okay, given that I've written this one word, what's the next word I should write? And then it'll say, okay, given that I've written this second word, what's the third word I should write? And it kind of goes in that manner, looking at what the model has already written, but generating additional text, right? So this is a decoder-only model. And then we have examples of encoder-decoder models where it slurps up a bunch of text and then is able to spit out a bunch of text. And the classic example for a model here is T5, which was a model released by Google. And the classic use case is for translation. So if I want to put in English and I want to get out Italian, that is a sort of classic case for an encoder-decoder model. Now, this is, I think, a good framework to understand. Are you squishing text into the model, and is text coming out of the model? And if only one of those things is true, it's either an encoder only or a decoder only. But if both of those things are true, you have a model that both has an encoder and a decoder. And this is helpful, and I think this is true, but recently it has become a little bit less useful for explaining the world. Because one thing that you may have noticed is, as I was talking about a decoder-only model, I mentioned that the model will look at text that's already written, right? It'll look at, well, I wrote these 7 words. What word do I write next? And on the one hand, this is different from feeding in text and having it spit out, basically unrelated text. On the other hand, if it's looking at the text that's already written, you are kind of feeding text into the model, right? The model is getting to see some text. And in fact, models like GPT 3.5, GPT 4 are purely decoder models. And that only works because you can put a lot of text in sort of the autoregressive history. You can have a whole conversation with stuff that you've put in there that it can then generate on top of. So the lines get a little bit blurry. But I think having this idea of, is there an encoder involved? Is there a decoder involved? And maybe there's an encoder and a decoder is, at least at first pass, sort of a helpful framework to adopt. So we are going to, and actually pop quiz here. If we want to go from a bunch of questions and answers, and we want to output one specific answer, so either A, B, C, D, or E, to you, does this sound like a job for an encoder, a decoder, or an encoder-decoder model? We just want to answer multiple choice questions. And I will wait until somebody says something. Donaker, you are absolutely correct. Or at least this is what I would say. As we mentioned, there's a fuzzy boundary, and there's totally a way to use a decoder-only model to do this job. But there's something natural about this that kind of feels like a job for an encoder. We have a bunch of text that's already written, and we want to feed it into a model and get basically a small numerical output. So we could just say, oh yeah, every answer is a 0 or a 1, and so it just needs to give us a set five numbers, right? For our five options, is it a 1, which means it's the right answer, or a 0, which means it's the wrong answer? Yeah, so this is, I think, a good comparison. Is like the shape of the data we're using here is kind of like sentiment analysis. We're putting a bunch of text in, and we're looking for a few numbers to come out. And this is one of those like silly ones where technically everyone is right. You really can use all these different architectures for this problem. But we're going to first start with what I think is the most natural fit, which is an encoder only model. And we were going to be using BERT. So BERT was, I think, like the first big transformer model that was made public. And when we talk about a model being public, really what we're talking about is the weights being publicly accessible. We will talk about something being open source, which means the source code for a program is public, which is already kind of a little bit of a silly notion because like a lot of code that's written is not actually compiled. It's just interpreted. And so the source code is kind of all there is. But you might write a lot of code to create a model. And then ultimately the thing the model is at the end of that process is just a set of weights. It is the giant matrix of zeros and ones that tells your model sort of how to process information. And so when we have this line right here, we are actually referring to over here a bunch of directories that have model weights. So we picked BERT base cased, which means, oh, not large. Base just means it is a smaller version of the model. And then cased, oh, that's uncased. Base cased. Cased means that it takes into account differences between uppercase and lowercase letters. So if you wanted to, you could get in here. And I believe the H5 there actually has like the raw models, which you can't show. But okay, yeah, we've got. It looks like a little bit like on the order of like a gigabyte or two. So relatively small in terms of the storage the weights take up. So we can just slurp this up. Another thing to call out for Hugging Face is there will usually be two big components of your model. You will have a tokenizer, and you will have sort of your model itself. So tokenizer just goes from having individual words, like actual language text, into a set of IDs. So every token will be turned into a number, and every number can get turned back into a token. And then separately, you will feed that into your model. And your tokenizer and your model always have to sort of be compatible. Generally speaking, you want your tokenizer to be the tokenizer that was used when your model was trained. So we have just slurped up a tokenizer. And so now what we're going to have to do specifically for our data set is to create a dictionary to convert our options into indices and back again. So remember, we were just saying, hey, we're going to get a set of numbers out, but our actual options are A, B, C, D, and we want to be able to turn those into zeros and ones. And so then what we're going to do is we will take, so preprocess takes an example of a single line in our data frame, and then you want to spit out the tokenized data that you actually want to feed to your model. Now, the way that Hugging Face is going to sort of want us to do this for multiple choice is to really have a set of a bunch of different options that all have the answer, the question and the answer. So all of our examples that we spit out are going to have the full question followed by one potential answer. And then there will be another line that has the full question followed by another potential answer. And we'll have one of these for each potential answer, because our model is ultimately going to be picking from a pair of a question and an answer, and which pair seems the most plausible. It's a little bit of a silly way to do it, but this is the way that it works best for feeding into our LLM. So what we have to do is we have to actually take our question, which is our first sentence here, and make copies of it in the same number that we have answers. So remember, we have 5 answers, and so we're going to want to take our examples prompt, which remember was like the actual question part, and then just duplicate it 5 times. So we have a list of that first sentence 5 times. Then what we're going to do is we're going to loop through all of our options, which remember are just A, B, C, D, and E. And then we can index in. So example right here is basically a dictionary. And so when we put A in here, it'll give us the first option. When we put B in there, it'll give us the second option, etc. And so we'll just go in there and take all of our examples, all of our example options, and append them to our list of second sentences. So our list of first sentences just has the question 5 times, and then our list of second sentences has each of our possible answers once. I better work in a warehouse. You know, there are lots of different jobs out there, and yeah, heady machine learning stuff. Not for everybody, not all the time. But if you have any questions, please drop them in the chat, and we can dig into it. So once we have our 2 lists of sentences, so our question 5 times and then our 5 different answers, we can pass it into our tokenizer. And our tokenizer is going to go from our actual natural language into, as I mentioned, a set of numbers. Now, the way that we often explain tokenization is that you're kind of just breaking things up into words, right? So, for example, I'll just show sort of a toy tokenization example. So say I have 2 sentences. One could be I like pineapple, and another one could be I like dogs. And then maybe a third one, we could say dogs like pineapple. Honestly, we should check that. Can dogs eat pineapple? Yes, raw pineapple in small amounts is an excellent snack for dogs. You heard it here first. So if we wanted to turn this into numbers, the sort of very basic way we could do this is we could just start looking at our words like, okay, I, and we'll map that to 1. And then we could say like is the second word we see appear. We can map that to 2. And then pineapple is the third word, so we can map that to 3. And then dogs is the fourth word, so we can map that to 4. And so, conclusion, I am possibly a dog. This is the peak of inductive logic right here. I appreciate it. We have not disproven that I'm a dog, I guess is, yeah, what we could say. So based on this dictionary of words to IDs, I could do something like saying, oh, no, I don't need emojis. This sentence could turn into 1, 2, 3, whereas this sentence could turn into 1, 2, 4. And then our final sentence here, because dogs is number 4, and then like is 2, and then pineapple is 3, we would say this is 4, 2, 3. And so we've just turned our words into lists of numbers. That's all tokenization is. In practice, you will actually not have a number for each word. You will have a number for each part of a word. So a classic example is I like and dogs might all be a single token, but pineapple probably is going to secretly be 2 different words or 2 different tokens. There will be 1 token for pine and then another one for apple. And that is, it's called subword tokenization. And it honestly was something that kind of blew my brain out when I learned about it, because I always had this question about like, okay, but what about super uncommon words, you know, words that only, you know, that would never appear in your training data set. How do you deal with those? And the answer is, well, you break them up into even smaller parts. We have a question, what will be the second sentence? Yeah, so for explaining what pre-processing we're doing here, I actually want to take another example. And actually, let's comment this out. Oh. So let's say I have a question that is, I don't know, let's say, what kingdom do fish belong to? And the answers are plants, animals, fungi, protists, astronauts. So this is our question. We have 1 prompt. So this right here is our prompt, and then we have 5 options. And so the thing that we're doing here is instead of just feeding this in one piece to our actual model, what we will do is we'll create a bunch of copies of it where we will say, what kingdom do fish belong to? Plants. What kingdom do fish belong to? Animals. What kingdom do fish belong to? Fungi, protists, and astronauts. And so what doing this sort of copying and rehashing is going to do, so in this case, this is sentence number one, and it's always the same. And then sentence number two is plants, animals, fungi, protists, astronauts. So what this allows our model to do is to basically just look at each one of these pairs and give it a rating. So it could say, that one seems kind of unlikely. This one seems more likely. We give it a 0.8. This one seems less likely. We'll give it a 0.05, and so on and so forth. So instead of just having one giant chunk of text, we're going to pair the question with each individual answer. So first sentence is always our question, and then second sentence is each of our individual responses. Okay, cool. This next block, I will explain conceptually a little bit, but I don't want to get into it too much. In fact, actually, no. Okay, yeah, this is the one block that I'm gonna kind of wave my hands around, mostly because I copied it from an example and I read through it. But it's not the most interesting bit of code. The main takeaway here is that when you feed a sample into a model, you need your sample to basically be a rectangle of some sort. You need it to be sort of everything that you feed in needs to be the same length. So one way you can imagine this is like if you're feeding an image into a model. Well, first of all, you have two dimensions where each line of pixels will be the same length as the next line of pixels. And even if you stack multiple images together, as long as they're the same resolution, you will end up with a bunch of things that are all the same shape. But with text, this gets a little bit harder because not every sentence is the same length, right? All of our questions are different lengths. All of our answers are of different lengths. And so what you want to do is you generally want to group things that are similar shapes together. So things that are relatively close in size together. And then you do a little bit of padding. So a silly example of this is if you were trying to put all of your books on a bookshelf, and you had one shelf that was really tall and one shelf that was really short, you would put all of your books that were pretty short together on the short shelf, and you'd put all of your books that are tall on the tall shelf, and you would still have a little bit of space on top of them, and that's padding, because ultimately the shelf needs to be a rectangle, or each individual shelf needs to be a rectangle. So what this data collation does is it takes a bunch of samples that are close to the same size and sticks them together, so you're not wasting a lot of sort of empty space. So what determines the score? Well, that is our model. That is our large language model that is spitting out that score. So we talked about the how many numbers come out. And so basically in this case, we're feeding it each individual example, and it's giving us one number of do I think this is correct? Yeah. So we're not coming up with that score. We are just prepping it so we can feed one in, and the model will be like, doesn't seem quite right. Then we'll feed another in, and it'll be like, oh, that seems like pretty likely. And then we'll feed another one in, and it'll be like, I don't think it's that right. I don't think that's the right one. Cool. So that's this whole cell here. I should actually be running these things. Cool. Okay, so we talked about the first chunk, which was our tokenizer, which we have used now. And now we want to create a model from our actual model weights. So we grabbed the tokenizer for BERT, and now we actually want to grab the model weights themselves. So this is kind of beyond the scope here. This is actually we're talking about do you get deep in on the math? But ultimately, once you get your input into a list of numbers, which is called vectorizing it, once you have just a list of numbers like your token IDs, the model itself is more or less a bunch of giant matrices that get multiplied together by your input. And honestly, in a way, artificial neural networks helped me understand matrix multiplication a little bit better, because all that multiplying by a matrix is sort of taking your matrix on the left side, passing it through a function that gives you a differently shaped vector on the outside, on the next side. And I don't want to be too hand wavy, but we really could do 7 live streams just on building the fundamental basis for what an artificial neural network is. But a lot those model weights tell you how to do a lot of complex math that spits out some output. This is where we start talking about your model here is kind of a black box. And you can do all that we're going to do without really grappling too much with the matrix algebra in the middle there. We'll run this. So these are some things that we've imported from Hugging Face, AutoModel for multiple choice. This just gives you a sort of a framework around your raw model weights. So individual models can do lots of different things, right? So BERT can be used for sentiment analysis. It can also be used for multiple choice, lots of different things you can use it for. And then we have our trainer and our training arguments. So we are going to slurp up from our model directory all those weights. And now in our model, we have something that is capable of doing multiple choice classifications. So one question is what does BERT know right now? We've gotten these weights in, and what is BERT just inherently capable of? And the simple answer is BERT understands a lot about the English language in this scenario, or we're using the English one, so the English language. It does not know a lot about the task that we want it to do, right? This will actually be a recurring theme, is that the thing that large language models understand is language. They don't understand like your goals or any specific subdomain, right? And so we have a couple options of ways to get them to do what we want to do. And the sort of the original way that we figured out how to make a sort of general pre-trained model do what we want is to train it a little bit more. So BERT was trained on essentially trying to predict the next word in a sequence. I think actually it was trained on predicting a masked word in the middle of a sentence. And so it understands something about relationship between words, but it doesn't know what a good question answer pair looks like or what a bad question answer pair looks like. And so a way that we can get it to understand this is the task we want you to do is to just take the examples in our training set and to show it all those examples and be like, hey, when I show you this correct pairing, tell me good job. And when I show you this incorrect pairing of a question and answer, tell me bad job. And that is the process of fine tuning. It already understands the basics of language, but we can show it a bunch of examples of the patterns in language that we want to pick up on. So that is what we're doing here. This chunk, this is at least a semester of machine learning. We could really do 30 minutes on each thing inside of here. So output dir, this is just where we're writing our model to. So we have slurped in the pre-trained model weights, but we are going to be updating those model weights to be fine-tuned for our task. And so we're going to spit out the updated weights into this model directory. Evaluation strategy. So an epoch is just means how long does it take you to go through all of your data. So if I give you a giant study guide and I want you to run through it 3 times, every time you get through the entire study guide, that is 1 epoch down. So this is a question of it'll evaluate itself at the end of every time it's looked at all the data, which we only have 200 samples in our training set, which is a pretty small data set. Save strategy is also epoch. So at the end of every epoch, it will save all of its model weights. But it'll also load the best model at end. So this will allow us to actually use whatever our best model weights are at the very end automatically. Let's see, we got some questions. Your data set already tags the correct answers for training BERT. Yes. Oh, yeah. So this is I'll scroll back just for a second. This is a point that we yes. Okay. So I totally skipped over this. So this is a great question. Is right here, we actually include in our tokenized example the label. So this is the thing that is correct, which we're actually passing in as a number because we're going from our actual answer to the option to index dictionary we built up, which turns our whatever our letter answer is into a number 1 through 5. And so actually one thing that we can do is we can, if we just want to take a peek at what's inside our data set, you can see that inside our data set, we have an ID, input IDs, token type IDs, an attention mask, and a label. And so we just look at one of those. So these are all of our actual individual tokens, which this is a little bit hard to see on one screen. I could scroll down, I guess. And then at some point, our second list is the token types, which essentially tell us, are we looking at like a question or an answer? And then if you scroll all the way down, you have your attention mask, which is what things are you allowed to look at. And at the very end, we should have our label, which is 3, which if you do the math, I think that means that the correct answer is D. 0 is A, 1 is B, 2 is C, and 3 would be D. Yeah. So that is the actual thing that we're feeding in. It has, both sort of the question in this tokenized form and then also the answer. Yeah, good call out. Good call out. So we're using a static learning rate. I mean, lots of, as I mentioned, this is sort of like an intro to trying to approach this problem. So your learning rate is basically when you get something wrong, how quickly do you change your strategy away from what you just did? And a very common thing that people will do is they will use a learning rate that gets slower over time. So maybe when you're first starting out, you do something wrong, you want to really, really commit that to memory, like, oh, I shouldn't do that thing. I should really change up what I'm doing. But then later on, once you've been studying for a year, if there's one little thing you get wrong, it's like, oh, maybe that was a weird question. I don't know, but like, I'm not going to change my whole worldview. Then here are some things for how much do we put on the GPU at once. I believe this is as big as you can get on our free GPU on Kaggle. They do give you a lot of free GPU time, which is a really cool thing that Kaggle does for people. Then train epochs. This is, as we said, this is like the number of times I want you to go through the study guide is 3. And then weight decay. I'm trying to actually remember what is weight decay? Training arguments. Come on. Weight decay. The weight decay to apply to all layers except all bias and layer norm weights in the Atom W optimizer. Oh yeah, okay. So we could get into optimizers. So optimizers are specifically the math of what direction do you take your next step in as you're trying to update your strategy. And weight decay is a way to control something called normalization, which is sort of it's a way of trying to guarantee that you don't learn the wrong lesson from a few specific examples, but we won't get too deep into it. Then report to is actually a helpful parameter if you are being a very, very serious adult where you want to do experiments and see the results of them. So there are lots of tools out there that will allow you to report all of the results of your training to them. So weights and biases is a big one where you can store information about your experiments, which is kind of cool. Cool. So those are our training arguments, but now we can actually build a trainer itself. So our trainer is going to be the thing that will actually allow us to update our model weights in order to be in line with this training data that we gave it, right? And so the simplest thing that we need is just the model itself. This is the thing that's going to be both making predictions on what the answer is and then being updated based on whether those predictions were correct or incorrect. Our training arguments is everything from above. Now, this is when you do a training, you want to have both a training data set and an evaluation data set. So you want something that it's actually learning from, but then something to test it on, hey, like, how well did you do? And usually you want these to be different data sets, right? The example that I use all the time is if your teacher gave you the test as a study guide, then you would probably not actually learn the material and just memorize the right answers. And this is why your teacher probably doesn't give you the test as a study guide. They probably give you something very similar to the test as a study guide, and then they have questions you've never seen before as the test. This is normally the thing that you want to do, but because we are just looking for a quick and dirty example, we are using our training data set, or tokenized training data set, for both training and evaluation. Then our tokenized that we already created, and then that data collator, this is sort of allowing us to use our GPU efficiently by getting questions that are really long and squishing them together, and then questions that are really short and squishing them together in the same way that you would put very large books on the same shelf in your bookshelf and very small books on the same shelf in your bookshelf to sort of store things more efficiently. So that creates our trainer object. And then, of course, finally, we can train. Now, I will throw out that Bert, I mean, at this point, Bert is 6 years old, I think, which in machine learning years, that's like 100 years, right? Bert is not right now the state of the art. It is a very small, very old model. But a thing that is really nice about that is because it is small, it can train really quite quickly. We don't have that much data we're training it on. But when I say this should only take about a minute to train, that is actually a really, really good, really, really good performance. I didn't want to use an example that was going to take 7 hours on stream to train, because obviously the stream would already be over. I love when you start training, because you can really see your usage graphs go kind of crazy. You're like, oh yeah, we're using all the GPU and all the CPU, and then we do a validation round and it stopped, and then they jump back up again. So good to keep an eye on this to see, am I really maxing things out? So you can see in our validation loss, this is a measure of how wrong are we. The specific number is less important, but the important thing is that you see the number going down, right? If the number going down over time, then you are actually learning something. And in this case, it looks like, yeah, we are, we're getting somewhere. Our validation loss is getting lower. Now, if your validation loss keeps getting lower, then you could imagine just continuing to train, which is often an okay thing to do. But again, we're just here for an example. So now we can actually make predictions on our data set. And that will, again, take some time. Not that much time, though. So now if we look at what our predictions are, they are a bunch of numbers, right? And remember, we said, hey, we're feeding in these 5 pairs of question, answer, question, answer, question, answer. And so in our first case here, this is basically the log probability that our correct answer is A. And here we have the log probability that our correct answer is B. And here we have that probability that it's C and D and E. And the lower the number, the less likely that is to be the right answer. So you can see in this first case, the model is like pretty sure it's A, but it's like, well, it could be B, right? And I guess actually this is for the second question. For the first question, it feels kind of bad about all of the answers, it looks like, which is kind of funny. But so if we look at, this is a case where it's relatively confident that the answer is A, or maybe it's B, we could actually scroll back up to our training data, and we could look at question number, like the second question here, and look at that. The correct answer is A. So it actually got something, it has something going on, right? It's able to understand on some level that A is the most likely thing. And then it was like, well, if not A, it would probably be B. But right now, we can't submit this to a competition. We can't say, hey, here are our results, right? This is what we think. Because this is, I mean, one, it's not human readable, and the grader is not going to interpret this giant 2-dimensional grid as actual answers to our test. But one fun thing, I am so glad that you think it's cool. I think it's cool as well. It's fun to see your model actually doing something, right? I will say something that I thought was fun about this competition is that the metric that we're using. So we haven't talked a lot about different metrics. One very simple metric is accuracy. So you could say, hey, your test is going to be graded basically with how many answers did you get the correct answer to? Or sorry, how many questions did you get the correct answer to? And if you had 100 questions and you got 60 of them right, you got a 60% or 0.6. That's your accuracy, right? But a thing that I was excited to play around with was, well, what if you give someone the option to actually manifest, I think it's A, but if it's not A, I'm pretty sure it's B. Because like in this case up here, so on the second question here, it was pretty sure that the question was A, but it really did say, hey, if the question isn't A, I'm pretty sure it's B. And so if the answer ended up being B, I don't think that I would say that our model was like surprised, right? I think our model kind of was leaning towards A, but it wasn't totally sure. And it kind of said, yeah, if it's not A, it's probably B. I wonder if we can find another example where it was more confident. It honestly looks like this one is one of the cases where it's the most confident. Not me, just looking at a bunch of random numbers. Yeah, I mean, honestly, that might be a case of higher than average confidence. But accuracy doesn't let you take advantage of that, right? Accuracy just says, was your top answer the right answer? And one thing that you can do is you can say, well, hey, what if we'll give partial credit if your second choice was correct, and we'll give even less partial credit if your third choice was correct? And this is called map at K. It is mean average precision at K. But really, the thing you need to understand is that for every question, you're allowed to submit up to 3 guesses. And if your first answer is correct, you get full points. If your second answer is correct, you get sort of half points. And if your third answer is correct, you get just a few points. Okay, Micah asks, is there a reason why all the cells in my matrix are negative? Good question. So by default, let's see, what's the right way to explain this? The simple version is just that the higher a positive number, the more confidence. And if all of your numbers are negative, your model just has like relatively low confidence about any of these answers, right? It is not sort of obligated to say, I think this one is correct. It could say like, yeah, all of these seem kind of unlikely to me. In general, these should cluster close to zero. And as you run it longer, so we could train for another cycle. It would probably take about another minute. And we would expect, after training another cycle, to have a little bit better separation where you'd expect in more cases, one of the numbers to be positive, meaning, hey, I think this is the right answer. And then the rest of the answers to be negative, meaning, hey, I think that these are unlikely. Yeah, school question for life. Maybe you did miss this bit, but it is a good thing to reiterate because it is the core thing happening here is that BERT underlying the thing that is BERT, the thing it understands is language, but it doesn't understand what we want it to do, right? It understands like what word might come next, but it doesn't understand the concept of I'm giving you a multiple choice question and I want you to evaluate each option and tell me which one has the highest likelihood of being true. And so what you can do is because it already understands the basics of language, you can just give it a few examples instead of, BERT was trained on hundreds of millions of words. But we can use just 200 questions and kind of give it the sort of final training, or fine tuning is the thing we call it, to update the weights and to get a fine-tuned model that is specifically good at answering multiple choice questions. Let's see, did we finish? Cool. So you can see here our validation loss actually kind of bottomed out. So maybe we have done all of the training that is actually going to be helpful for us. But we can check again to see, have we made any progress? Okay, so line 2, this is a good one where all of them are negative except for one. So right now our model is like actually quite confident that A is the correct answer for the third question. And it seemed like it got more confident than last time, which is good. Cool. So we have these predictions of here's my, here's the ranking that I give A, here's the ranking I give B, here's the ranking I give C. Positive number means, a higher confidence. But we really want to go back to just a list of, this is my top guess, this is my second guess, this is my third guess. And this function right here does just that. So we take our negative predictions. So one way of thinking about this is by default, the way that you sort things is from low to high. But we really want to sort things from high to low. And so by multiplying everything by a negative here, we can functionally say, reverse the way that you're sorting. So this gives us the sorted answer indices. So actually, maybe we should look at argsort for just a second. Let's import NumPy. And argsort. So argsort, I think we actually should be able to pass just a list. Maybe it will yell at us for passing just a list. No, it's okay with just a list. Great. So what argsort does is it sorts your list, but then it gives you the indices of the original things. So let's say that that we have a list of 1 for, let's just do 1, 150. And so what argsort is going to do is it's going to tell you the thing at the 1 index was the highest, or really it'll tell you the thing at the 0 index was the lowest, and then the thing at the 1 index, or at the 2 index, was the next lowest, and then the thing at the 1 index was the last lowest, sort of. And so it'll give you the sorted indices. So it'll say, well, yeah, 0 was the lowest, and then 2 was the next lowest, and then 1 was the highest. So instead of sorting the values themselves, it sorts the indices of the args of the values. Yeah, a linear sort that returns the index. Yes, this is a good way of phrasing it. I endorse this phrasing. So what this is going to do is by arg sorting our predictions, but in reverse, it'll say, well, hey, if C was the most likely, then I'll return a 2, right? And if D was the most likely, then 3 will come first. And so it'll give us sort of these numbers. It won't give us letters yet. It'll just give us numbers, but it'll give us in the order that it thinks they're likely. So then we can just use some slicing. I don't know if anybody is unfamiliar with slicing. We could talk about slicing if you want to talk about slicing, but this just gets all of the rows and then just the first 3 columns in each row. So that gives us our top answer indices. And then this is honestly kind of a silly bit of Python, but the thing that it is doing is it is using our index to option dictionary that maps 0 goes to A, 1 goes to B, 2 goes to C, and so forth. And it just uses that to turn all of our actual numbers or our indices back into letters. And then finally, this just says, turn all of that. We now have a list of letters, and I want you to join them up into a single string of guess number 1, guess number 2, and guess number 3. And so this will give us, if we run this on our predictions, we should get a bunch of strings that go ABC or DBA or ACE or whatever. And if we run it, that's exactly what we get. Huzzah, we're very happy. So you remember our second question was, it was pretty sure it was A, but it was like, if it's not A, then it's probably B. And in that case, it was in fact A, and it feels good about that. And then it guesses B, and then it didn't really care after. If it said if it wasn't B, I don't really care. But technically, C was the next most likely thing, so it gives us our 3 guesses, and that gives us our predictions. So now we can ingest our test data set, which in this case, our test is actually the same thing as our train, but it doesn't have the answer in it, so we can treat it as if this is the test set. So you can see it just has prompt A, B, C, D, and E with no answer. And if we just were to give our answers, our test a random answer, we would be able to make predictions with it to give it a field. But we can then pass it, basically do the exact same thing that we did for our training data set and map it into our tokenized test set, which should take a second. Then we could run our predict function on it to get our test predictions. And then finally, we can create a submissions data frame that just pulls out the ID. So when you submit on Kaggle, they don't want you to include a bunch of extra unnecessary data. They just want you to put in the IDs and what your prediction is. So here we have our test predictions are just that list of numbers there. But then we can grab the ID of each of our individual questions, and then we can turn our prediction numbers into our nice output where it says, A, B, C, or DBA, or whatever, and put that in another column. And if we do all this, we should get a nice little data frame that has our IDs for each question and then our predictions for the answers. And then if we run submit, this would submit to the competition. Now, as I mentioned, competition just closed a week ago. I will say I actually got the date wrong. I thought that this was going to be last week, and it would have been like perfect timing. But as it were, I think still a very, very fun example. And you still can, well, I actually don't think you can click submit. Can you? Okay, it looks like you actually still can submit if you want to. It just will not actually, you won't be considered, to be a winner, I suppose. Sakshi, I appreciate the kind words. I enjoy coming on here and streaming with y'all. Okay, so all of this was looking at an encoder only model, right? And as we mentioned, I think that for multiple choice questions, an encoder only model is kind of the natural fit. You are going from, a bunch of text to basically one number result or a couple numbers as a result. But as we mentioned, these days you can use a decoder only model. And because it is looking at sort of the history of the text that it has written, because it is autoregressive is the word we use, it can always, you can always stick some stuff in there and get it to generate on top of it, right? So this is, if you are just predicting the next word, well, if I give you a whole question that says, answer this question, A, B, C, D, or E, then maybe the next word that you will write will be the right answer, right? And that is sort of what we're banking on if we are trying to, that is what we're sort of banking on if we are trying to use a decoder only model. Okay, this is actually a great question because this is something that I've been thinking about a lot. So I have been looking at the winning submission, and you can actually come and click over. A lot of people, I think it's a cool thing about Kaggle is if folks that win, they will often share their results. And there were a couple that I would highlight. So this was actually the first place. Fourth place also had a pretty good write up, and generally what I would recommend, or I don't know how to say recommend. Sometimes reading other people's code sucks. I think this code is relatively readable, but I don't want to take too much time doing it. So I will just sort of give you the Will's short summary, which is they used both a really really good model where the weights were tuned, like really really tightly, but they also generated a bunch of their own training data. So what a lot of people did is they said, okay, we're going to try to train our model on science-based questions. I am going to go and generate a bunch of additional science-based questions. So instead of just the 200 that you give us, I'm going to generate, 40,000 science multiple choice questions and train the model on all of those. And you can imagine that it's like, well, hey, if a question that I'm asking in the test set has appeared similar to it in the training set, then that's going to make the model perform better on it. So that's thing number one, is they just generated a lot of data, which is neat. And actually, a lot of them generated a lot of data and then also shared it, which was very cool. But the other thing is that a lot of people used information retrieval techniques. So this is kind of like saying, if you ask me a question, I'm going to go Google the question you asked, grab whatever thing is the first result, and then put it in the model as some context for it to depend on. Or like another way of putting it is like, okay, the question had the word gravity in it, and I'm going to get the Wikipedia article for the word gravity and just include that in the context that the model can see when it's answering this question. Those, I think, were the two big methods that I thought were neat. Whereas one, generating a bunch of additional data to feed in there, and then two, doing information retrieval so that it would actually look at the question and go and try to find relevant context and include it in the context for the model that was going to generate the answer. That's an interesting one. So you mentioned you could try translating the data to get more out of it. I will say, on the one hand, I don't think so. All of our questions are in English, and there is like a lot of interesting work done on translation or having a model that itself is multilingual. So I think that if you can go, even though it didn't specifically train to do this, like you can go and talk to ChatGPT in Spanish, right? It'll talk back to you in Spanish. It knows Spanish, even if they don't want you to know it does, right? But because specifically we knew that all of our questions were going to be in English, training your model on things that were not in English generally wouldn't be helpful. But this idea of trying to do something with the data, the word for it is data augmentation, where you can, like, one sort of not silly, but like a sort of naive strategy you can use is get a giant thesaurus, and for every question, if there are any synonyms for a word in that question, change it to the synonym and then also include that as a training sample, right? So it can make your model sort of more robust to if the question was phrased slightly differently, which is sort of a riff on this. You could do the thing where you translate the question into a language and then translate it back to English, and you get slightly sort of another method for getting some paraphrasing. So this is actually a super interesting question, and the answer is like yes, sort of, but it's not that crazy. So there is this idea in linguistics of like a pivot language, right? Of if you want to translate 100 languages between all of them, if you wanted to translate from each of 100 different languages to each other of the 100 languages, technically, I think it'd be like 100 squared, right? Or 99 squared. And 99 times 99, because I'm not very good at math, call out, is like 9,800, like almost 1,000. But if you said, okay, all of these, like let's pick a pivot language. Let's say our pivot language is Esperanto. And we'll just translate, whenever we want to do translation, we'll translate everything into Esperanto and then everything out. And then you only have to build 200 translators. You need to be able to translate everything to Esperanto and then Esperanto to everything, but then you're done, right? Then you can translate between any two languages. Now, what Google Translate does is a little bit different. So if you remember when we were talking about encoder and decoder models, and I threw out, if you're doing sentiment analysis, you just need the encoder. If you're doing text generation, you might only need the decoder. But translation is a really good example where you have an encoder and a decoder. And the thing that is cool, that I believe the thing that you're talking about is that your encoder and your decoder are basically like Legos, right? So you have one thing in the middle, which is like, this is what your state looks like. This is how you understand a sentence, which is, a giant set of numbers. And you can build an encoder decoder model in a way that maybe one side is encoding English and the other side is decoding German. But then you could rip off the German decoder and instead put in a decoding Japanese, right? And then suddenly, you just by adding one Japanese decoder, you can now translate from any language into Japanese. And so it's sort of an inevitability of the architecture that you end up with this sort of hidden intermediate state. But this is, I believe, probably what people are talking about when they say Google Translate creates an intermediate universal language. But I think it is very, very neat. Okay, cool. Yeah. So you had this whole idea of exactly data augmentation as a path. Ultimately, data augmentation in this kind of task doesn't get you that far, but it is like a thing that you can use for sure to make whatever data you have go a little bit further. Cool. Okay, so now we're actually making great time. So now this has all been on the encoder only model side, but then I wanted to look at to play around with a decoder only architecture, because in so many use cases, decoder only architectures, they're the hot thing, right? Your GPTs, your Bards, your Claudes. Are there any other big models that I'm forgetting? I think those are actually the big ones. I guess I mentioned Palm, Bard, kind of the same thing. And Hugging Face, we used Hugging Face in sort of a tinkering with the insides way, where we were, kind of poking and prodding and calling a sort of specific model architecture. But Hugging Face does also allow you to use this thing called a pipeline that basically wraps around all of that funky in between stuff and just gives you a really, really simple interface that you can call. And that is called a pipeline. So we can use a pipeline called a conversational pipeline, which by default, I believe it uses a Microsoft model that's relatively small and can run on Kaggle hardware. But so we can import we don't need this import. We can import pipeline and conversation as a data type. And this is going to allow us to engage with a conversational LLM that is, there you go, Dialogue PT, I don't know. And so now that we have this pipe, we can feed stuff in and get stuff out. So the sort of most basic thing you can do is you can create a conversation with this conversation object and then pass that conversation to your pipe. And when you pass that conversation to your pipe, you get this little output. So you get, hello there, how are you, is what I passed in. And the bot responds, I'm good, how are you? Cool, we can chat with our bot, love it. But now we could try to pass in a multiple choice question. So our prompt could be, what planet is fourth from the sun, Jupiter, Pluto, Earth, Mars, Venus, right? And we could pass that conversation we could pass that prompt into our conversation, and then it comes out into our pipe. And unfortunately, we get, I think it's the planet that's closest to the sun. Now, this is what I'm talking about when I say the model can understand language, but it doesn't understand the task that we're trying to get it to do. Now, you or I can look at this and be like, oh, multiple choice question. Like, probably I am being asked to respond with D, that Mars is the fourth planet from the sun, right? BLM is just like, is kind of riffing and is just doing the thing that kind of sounds the most probable, but does not know the thing we're trying to get out of it is specifically responding in this structured way to a multiple choice question. What is TensorFlow? It's just like Hugging Face. Ooh, okay, this is a can of worms. The simple version that I would give is that TensorFlow and PyTorch are sort of lower level libraries that allow you to do sort of the initial creation and training and low level tinkering with models. And then Hugging Face is like this wrapper around things like TensorFlow and PyTorch that allows people to not deal with the nitty gritty as much and sort of just use the models without necessarily having to assemble the models themselves. So as we said, this by default, out of the box, this model is not actually responding in the way that we'd like it to. But we could answer we could just add to our prompt and just tell it exactly what we want, right? We could just ask specifically for the kind of response we want, and we could say, answer only with A, B, C, D, or E. So we're telling it to actually pick from the list, right? And we can run this, and unfortunately, it does not wise up. It does not understand us telling it explicitly is not going to actually give us the right answer. And this is, I think, it's actually one of the cooler things to have come out of LLM research. There's this idea of few shot prompting, and this is basically the idea of show don't tell. I think this is true for LLMs and for humans. Is that oftentimes instead of telling someone exactly what you want them to do, you should just show them, hey, this is the thing that I want you to do. Just like do what I did, right? And so what we can do here is we can basically inject an example into the history of our conversation with our bot, and it will learn from that it's like, oh, what's likely when I'm presented with a multiple choice question? I guess the most likely thing is for me to answer with a letter. So the thing we can do is we can keep using our prompt as sort of our initial conversation, but then we can just append the response D. So we're just saying for this first question, we're just saying that the model answered D for us. And so if we run the conversation through the pipeline, we'll see, okay, yes, the bot responded like we sort of forced it to with D. But now we can keep that conversational history, and we can get an additional prompt, which is what does ice turn in when it melts? So another multiple choice question: fire, air, water vapor, Michelle Obama. And we can add that to our conversation. So we're not creating a new conversation. We're just saying this is sort of the next step in the conversation. So this is an example of few shot prompting, where this is the real question we want it to answer, but then we're giving it an example of the way we want it to answer, or the way we want it to answer this kind of question. So when we give you a multiple choice question, respond with just a letter. And we are now giving it another multiple choice question, and we can see, will it actually sort of take the hint and answer in the way we want? Oh no, this is tragic. Okay, I will be totally honest. I was playing with this, and it was doing the thing that I wanted. That's weird. I'm not sure if I should upvote or downvote this. That's interesting. Maybe we do need to. Yeah, this is the tragedy of doing it live. Let's see. I wonder if we just use a new conversation without having it weigh in. Bert just became a Twitter troll. Okay, well, to be fair, this model is actually in theory like quite a bit more powerful than Bert. A lot more recent at least. Oh, that's quite tragic. So, we have our prompt and we append D. We can, of course, just try adding one more example, which is maybe worth trying. So here, let's add one more example where we say, I don't know, what's a good science question? What is the acceleration due to gravity on Earth? And let's say 1, 9.8, 2, 3, 4. And then we can append the correct answer here is, of course, B. Cool. I'm not sure what you're asking. Oh, okay. This is a bummer. I will also say I'm actually using a slightly old version of Hugging Face. The one thing that I will try is restarting and then let's pip install transformers. So if you are using a library that you care about having sort of the most recent version, you can run pip install transformers, um, and this should give you the sort of the most recent version. Or you could actually we could dash dash upgrade. And then I believe if we end up using the most recent version, we can use a slightly different method where we can add messages to the conversation a little bit more powerfully. Cool, downloading our model. Okay, cool. We get user and assistant, which is nice. And so now I think we should be able to, wow, let's try this. Okay, cool. So we see the same behavior, and we can try the modified prompt, but it probably won't work. Yep, we see the same behavior again. And so now we should be able to, instead of append response, I think we should be able to say add message. And then here, instead of just the answer, we can say both who is doing it and we can say like basically the speaker and the thing that the speaker is saying, which actually I'm going to double check this. I'm going to do it live. Conversational pipeline Hugging Face. Conversational pipeline. Okay, yeah, add message, and you can pass role and content. Great. Add message, and we can say role is assistant, and then content is D. And then we can add another message where role is user, and then content is our question. And then we will add the final message where we will say role is assistant, and then content is the right answer, B. Let's see if that all works. Oh, did I have a missing? Oh, I need to close my dictionary. Boom. Okay, someone asked, is the idea for the pipe to give the correct type of answer or get the correct answer? So in this case, this is the whole idea, is that we're showing it examples of what giving the correct answer looks like, so that hopefully it will give us the correct answer in the format that we want. Okay, cool. I guess we do have a sort of a dangling new line here, which shouldn't be weird, but we try that one more time. Let's see. Is there some kind of user acceptance testing for trained models after running these modifications? We're asking one question, finding an issue, but how extensive is the testing for any model that took a while to train to figure out if it's any good? Yeah, this is a great question. This is the whole field of machine learning research right now. Honestly, is this how can we characterize these things? That it's this weird way in which I mentioned earlier. It's like, oh yeah, a lot of the questions that people ask in machine learning research right now, they almost sound more like psychology or sociology questions, because it's almost like we were computer scientists and then suddenly we discovered this alien species, which is this LLM, right? And suddenly the task of figuring out how does it behave, how is it going to respond to things, is it going to be cooperative, is it going to be racist, all these questions are suddenly these big areas of research. And people have lots of benchmarks. So for example, the idea of like seeing if it can answer a lot of science questions, that tells you one kind of thing about it, right? You can just run all this data against it after you've trained something. But there are lots of other benchmarks. And then there's actually a thing called, I think it's called LLM Arena, which is where two LLMs go head to head and users get to pick which response is sort of a better response. And you can sort of use user preference this way. But yeah, it's a great big question, and it's kind of where the field is at right now. Cool. Oh, we don't actually want to do that. We just want to generate the conversation and then just see what it looks like, which is great. And so now we can add message, which this one will be the actual message. And so we'll say role is user, and then content is our additional prompt. And great, so we have two examples of how to answer a question, and then the big reveal is, will it answer the question in the way that we want? Which is just giving us a letter back. Oof, I'm not sure if I should upvote or downvote this. So a couple caveats here. I think we're gonna leave this here, but a couple caveats. So one is, obviously, this is not the biggest, strongest model ever. This is, I think, the size of it is a little bit under a gigabyte as well. So in terms of just the overall size, it's not that big. It doesn't have a lot of capacity, but also this is one of the challenges with prompting as opposed to fine tuning. When it comes to fine tuning, you really can kind of tell a model exactly what you want, and it's like you're doing brain surgery on the model, right? You are going and messing around with the neurons and being like, that neuron that was not doing the thing I wanted, we'll rewire it over here. And you end up with a lot of control, but it can also take a lot of time and energy and resources and data, right? And on the other hand, prompting can be really, really powerful. You can sometimes get just what you want just by asking, right? I mean, this is the joy and the power of things like Bard and ChatGPT. And on the other hand, it can be less reliable, and it can be really hit or miss, right? You can even show it several examples of the way you want it to respond, and your LLM might not do exactly what you want. And this is actually one of the big things that I wanted to show off, was just this difference between few-shot prompting and fine-tuning, and the difference between encoder and decoder models. But yeah, this is what a prompt engineer does now, is goes and toys with a bunch of different things. And it's like, well, if I format it a little bit differently, if I phrase it differently, if I say please, if I say unpack this step by step or whatever, can I get better performance these ways? And I'm sure we could do that for another 6 hours. But I think I'm going to leave it there. Let's see. King C asked, how did ML AI as we know it even start? Yeah, that is a great question. I actually should get together and here's my 5 minutes doing the history of machine learning, because it is kind of a cool history. This is unrehearsed. I think the big things in my mind are there was the era of quote unquote good old fashioned AI, which is you just write a bunch of rules about what you want your machine to do. There was specifically a really good, a really interesting model. I think it was called Eliza. That was quote unquote good old fashioned AI that would talk to you as a therapist, but all it would do was you would type in something and then respond with something like, and tell me how you feel about that. Or it would maybe pattern match on a few things. So if you mention your brother, it might say, and what is your relationship with your brother like? It had a few other rules like this that it would try not to repeat itself. It would try to vary its word choice. But that was sort of the state of AI, was just, I'm gonna take in some data and I'm just gonna write a rule to respond with something. And then there was something called the quote unquote Great AI Winter, which was where we hit a lot of sort of plateaus in making progress. And a lot of people said maybe we're not thinking about this the right way. Maybe we need to go to the human brain. Maybe we need to look at how nature organizes itself. And the research funding kind of dried up. And then, interestingly, the thing that kind of reinvoked AI and machine learning research was gaming, and the development of the GPU for video gaming. I think was actually one of the biggest unsung heroes of machine learning. Is that once you had these things that were capable of doing just a bunch of matrix multiplications in really short periods of time, you were able to make these models just much bigger. And a lot of the ideas that we had, artificial neural networks, have existed for like 40 plus years, but they just didn't really work that well until you were able to make them pretty big and run them on GPUs. And so that, I think, reinvigorated sort of a lot of research. And so you got additional architectures like the recurrent neural net or the convolutional neural net, which were sort of ways of figuring out how to get this data into the neural net in sort of the most efficient way. And then in 2017, you have, I think this 2017 paper, Attention is All You Need, is genuinely sort of like one of the single biggest jumps forward in machine learning, which it doesn't introduce this idea of attention, but it says attention is all you need, which sort of lets your model look back and forth at the input. And it can say, well, when I'm looking at this word, really I need information about that word back there. And when I'm looking at that word, really I need to think about the 2 sentences ago. And this attention mechanism, which is the basis of the transformer architecture, was really this giant leap forward. Then after the transformer, there was a lot of research that I think it was a relatively smooth slope up to the point of I think the last big milestone was the sort of public release of ChatGPT, and the on the one hand, it didn't represent a massive scientific breakthrough, but I think it represented like a massive sort of product breakthrough that like you can just put an LLM in people's hands and they will play with it, and like it'll be interesting and compelling, and like it'll do things for them. That's like maybe my 2-minute version of the history of machine learning. Have I used Llama 2? I have played around with Llama 2. Yeah, Llama 2 is actually is one of the baked-in models on Kaggle now, so it's relatively easy to grab those model weights. I will say, here is one specific thing that I have faced some trouble with Hugging Face. I think actually the conversational pipeline is really nice, but when I have been playing around with particularly some of the decoder-only models like Llama 2, knowing the format that they originally constructed their prompts in. So like if you see on I'll pop back over here, we have user and assistant as these little prefixes. And when you just get like the raw model that's not wrapped inside this pretty API, you're just feeding it raw text and getting the next word out. And so you have to like go and hunt down like, oh, when they were building this model, did they call the user? Did they call the user human? Did they call the assistant bot? Did they call the bot assistant? And like figuring out what format you want your prompts to be in to match the way the model was trained, to me has ended up being like a headache that requires tracking down papers and being, and it's silly because it seems like a thing that should be really accessible because people are using these models. Let's see. Yeah, I mean, this is, I don't know, I feel like this is kind of the metathesis of this stream, is that the thing that BERT understands from consuming a giant corpus is just the way that language works and nothing about like the goals that we have for it, right? There's actually a thing, I think it's called Wernicke's aphasia. I'm gonna see if this is the right one. Okay, yeah. Look up, or also called fluent aphasia. I think I'm going to drop this link in. Okay, yeah. So this is a condition that that faces some folks. There's a thing called Wernicke's area that deals with sort of semantics and what words mean, but it doesn't necessarily deal with grammar or syntax or speech generation. And so you can talk to folks that have this kind of aphasia, which is trouble speaking, and they will sound like they are speaking English. You'll be like in the cadence and the tone and the flow of how they're speaking will totally sound right. And then if you pay attention to the actual words, you'll be like, oh, actually the words that you're saying don't actually semantically mean like at least the thing that you are trying to get across. Anyway, a way of thinking about this is that these large language models are essentially very intelligent folks that have Wernicke's aphasia, where they kind of understand how language is supposed to sound, but they don't understand anything about the task that you want them to accomplish. And so the point of fine tuning and prompting is to try to get these models to understand the task that we have for them. Has MLH considered doing hackathons for existing FANG engineers? That's an interesting question. I don't know. I know that, I mean, I think that happens a lot is that engineers from, large companies end up going to hackathons as mentors and like in a formal capacity. I've gone to half a dozen hackathons like on behalf of Google to go and, pass out t-shirts and stuff. So I think that that's sort of a natural reason why there's not a mesh there. I don't think that MLH has ever done a hackathon. They have done hackathon. That's not true. There have been collaborations with companies to do internal hackathons. I believe there was like a hackathon with some crypto companies in, oh gosh, there's an island nation in Europe that does a lot of crypto things. So there have been some collaborations like that. I don't remember what this is in response to, but I like it and I think it's a good idea. Yeah, I think inter-company collaboration is very tricky. Mostly just because this is like something that I had a slight sense of before, but not real like learned a lot about after interning at Google. Really was the degree to which like it's mostly security, right? It's the, hey, like no person who is not an employee of this company should be looking at your laptop screen, say, right? It's like, oh, you do a hackathon. It's like that's the whole thing is people looking at other people's laptop screens. And so I think it's sort of a natural sort of legalese reasons that that sort of thing doesn't get off the ground. But I mean, it sounds like fun. Oh yeah. Okay. Cool. This is what I'm talking about. Is like you can see research of like, hey, they had an artificial neural network in the 50s, right? And it's like, where did that go? And yeah, the truth was it was big and unwieldy, and it couldn't do much until you got a billion of them. Kind of like Simlish. Simla. What is Simlish? This isn't a Lord of the Rings thing, is it? Oh no, Simlish is what Sims speak. What is? Oh, it's the Cimmerillion is what I'm thinking from Lord of the Rings. Yes. Oh yeah, kind of like Simlish. Yeah, for sure. Respectfully. I am new to the general scope of hackathons. How can I usually participate in one? Great question. This is really making me put on my MLH cap. Sorry, my dog Darwin is barking very loudly, and it is distracting. There are a couple big good ways. One is if there is a university, if you are a university student, or if there's a university near you. Usually, they will host one at least once a year. Most medium to large size universities will have a hackathon, and that is, I think, one of your best bets. For me personally, I think there's nothing like being in person at a hackathon and going to a place. I think can be really, really powerful. And most of these hackathons they'll primarily focus on students at that school, but they will be open to people that do not go to that school. So it's a great way. I mean, in college, I had a group of friends, and it's like every other weekend we'd like drive 6 hours to go to a hackathon at a different school, and it was a lot of fun. So that's also a thing to recommend. There are a lot of online things. Obviously, I mean, MLH will host virtual hackathons, and you can go to mlh.io to see things. Let me grab that for you. Boom. But yeah, those are some of the ways that I would recommend. Also, things like Global Hack Week. It's not like exactly a hackathon per se, but at least for me personally, I feel like I get some of the similar energy. I was referring to the use of nation model AI. Oh yes, absolutely, yes. This is actually my favorite, unequivocally my favorite class in undergrad. It was called Biologically Inspired Computation, and I thought it was just the best. And it was looking at, I mean, artificial neural networks were a big chapter in this, but it was also looking at, like, how can we model routing packets on the internet with the way that ants will find their way back to their anthill. Anyway, I think that sort of conversation is very cool. Anujan asks, will there be no leaderboard this time? Yes. So this is actually, this is unfortunate, but I have just been swamped with work recently. And so I am not doing a full track this week. We are just doing this one-off on using open source LLMs. This was it. And then on Thursday, I will be back for an intro to Python. I think that we will, if you attended this and you have like additional questions, we can totally talk more about open source LLMs or machine learning in general on Thursday, because I imagine the intro to Python bit will be relatively contained. But yeah, thank you so much for being here. I will hang on for just a few more seconds in case there are any other questions. Y'all's engagement has been chef's kiss today. It is really fun when people bring their A game and like have interesting things to talk about, especially in a setting like this where it's like the content is is relatively straightforward. But y'all have been incredible. I don't see any other questions. So hopefully I will see you here again on Thursday. But if not, thank you so much for hacking with me, and happy Global Hack Week, y'all. Take care. Bye.